Hello everybody. In this video we will give somewhat less standard examples of vector spaces and the example that's of particular importance to us, one of a field extension. So let's begin with the following example. So this is a continuation of examples of vector spaces over various fields. So in this case, I'm going to take V to be the set of polynomials with coefficients in Q whose degree is less than or equal than 3 and the zero polynomial. Remember that we did not assign a degree to the zero polynomial, so I have to throw it in. This condition does not include the zero polynomial. Okay, so how do the elements of V look like? Well, they look like this: ax cubed plus bx squared plus cx plus d, where a, b, c, d are all rationals. Note that this set this set is not a ring in any natural way, because if I just use standard addition and multiplication of polynomials, then if I take any two polynomials, or if I take, say, polynomial of degree 3 and a polynomial of degree 2, I would get a polynomial of degree 5, and polynomials of degree 5 are not contained in this set. So this set is not closed under multiplication. So it is not a ring. It's not a subring of the ring of polynomials with coefficients in Q. It's only a subset. However, I claim V is a vector space over Q. So clearly when I add two polynomials of degree less than or equal to 3, I get one of those polynomials. So the set V is closed under addition, and now I'm defining scalar multiplication when I say, well, if I take alpha in Q and I take such polynomial, then I just define this to be alpha a x cubed plus alpha b x squared plus alpha c x plus alpha d, where alpha is in Q. Okay, so this defines scalar multiplication on this set. It's sort of a you would definitely define it like this, right? It's nothing strange about this. Which means that this polynomial is that this set is a vector space over Q. This scalar multiplication, certainly if this polynomial is of degree less than or equal to 3, then the resulting one is also of degree less than or equal to 3, and you can check that it satisfies all the axioms. We're not going to do that. So some things about this that you could actually specify. So one question that we would often like to know is, what is a basis? You know, there are many possible bases of this of any vector space. So we would like to find a basis for this, or maybe give an example of a spanning set. So, you know, a very simple example of a spanning set is this. Well, I can take the constant polynomial, the polynomial x, the polynomial x squared, and the polynomial x cubed. And clearly, every polynomial of degree less than or equal to 3 can be written as a Q-linear combination of these monomials, right? So this is definitely contained inside V, and it is a spanning set. In particular, right, if I want to write, I mean, I'm sure that you already understand what this is about, but if I wanted to write this polynomial using this spanning set, I would just write it as, okay, I'm going to write different colors for scalars and different colors for vectors. So so this would be equal to, and now I need to use these vectors here. Well, okay, so I'm going to use 1 and x squared, and then the coefficients would be -1 and then plus 3 and then plus 1. Right, these are coefficients in Q. And the red things are the vectors, so they are in there. So we call the spanning set W. In W and in W. Note that this is actually also a basis, because there's no linear dependence between these. If I was to try to find coefficients, 1 plus x plus x squared plus x cubed to get the zero polynomial, right? If I was just trying to find alpha, beta, gamma, and delta with alpha, beta, gamma, and delta in Q, you know how polynomials work, right? In order for this polynomial to be the zero polynomial, all these coefficients have to be 0. So this implies that alpha is equal to beta is equal to gamma is equal to delta is equal to 0. So the spanning set W is also linearly independent. So is a basis of V. So as a conclusion, right, we get that the dimension of V over Q is 4. Actually, something to be expected. Let's do another example. So example 3, I'm going to take V to be all the complex numbers. And I'm going to treat these complex numbers, I claim this is a vector space, then V is a vector space over the reals. Okay, so first of all, complex numbers are a field, so they come naturally with addition and multiplication. I'm going to completely ignore the multiplication and just focus on the addition. So I'm only allowing the complex numbers to be added, but then also I would allow them to be multiplied by real numbers. And of course you know that if I take a complex number and multiply it by a real number, I get another complex number. So that will be my scalar multiplication. So, I mean, in particular, right, so if alpha is in R and I want to define the scalar multiplication, I do it this way. So this is in C, A and B are in R, and this is a scalar in R. Could we find the basis of this? Yes. This isn't very difficult. Namely, what two complex numbers can I use so that every complex number would be a real linear combination of these two complex numbers? Think about it for a second. 1 and I both certainly are complex numbers. And now you agree with me that every complex number can be written as a real number times 1 plus a real number times I. So that means this is a spanning set. On the other hand, it's also linearly independent, because if I write alpha times 1, so alpha plus beta I to be 0, and alpha and beta are only allowed to be real, the only way for this to happen is if alpha and beta are both 0. So this set is both a spanning set and it's also linearly independent, so it's a basis. So the complex numbers, the dimension of them, is 2. And this is, of course, just a manifestation, or a manifestation of this is the fact that whenever we want to geometrically represent complex numbers, we actually use a plane. So a plane geometrically is the same thing as R2, so a two-dimensional vector space over the real numbers. So the complex numbers geometrically are represented by a plane, which is two-dimensional over the reals. So that shouldn't be surprising. However, note that this V can also be thought of, then V is also a vector space over C. Over C. Does that make sense? Well, C is also a field, so we can also consider this as the source for scalars. The addition being the same inside complex numbers, and then the scalar multiplication. Well, in this case, the scalars are the same as the vectors, so I just define the scalar multiplication to be just the multiplication in C. And you can again check that it satisfies all the axioms. In this case, the basis you can choose any non-zero complex number, for example 1, because clearly every complex number can be written as a complex number, so scalar, times 1. So dimension of C as a vector space over C is 1. And this is kind of a crucial example for us, because C actually started life not as a vector space over anything, but as a field. And we treated it, we took a subfield of the complex numbers, namely the real numbers, and we treated them, these complex numbers, as a vector space over this subfield. And it turns out that that's always the case. And that's what the title of this talk is about. It's sort of the most important example for us. And it's really a key observation in studying all these field extensions is this. What we just saw in the case of complex numbers. So key observation. If K is a field extension of F, then we can treat K as a vector space over F. I can't overemphasize the importance of this observation. To have a vector space, you need to have two operations: addition and scalar multiplication. What will be the addition? So K is our V, right? This is sort of secretly our V. What is the addition in this V? Just addition in K. K is a field, so it comes with an addition. What's the scalar multiplication? So I have to tell you how to multiply a scalar that comes from F by a vector that comes from K. And the thing is that so the scalar that lives in F can also be treated as an element of K, because F is a subfield of K, right? Or K is a field extension of F. So everything that lives in F also lives in K. So I can take this element of F, treat it as an element of K, and then multiply this element by another element of K using the multiplication in K. Yep, so addition of vectors is the addition in K, in the field K. Scalar multiplication what do you do here? As I just explained, if alpha is in F, and then I'm going to write V. We never really write V for elements of fields. I would just write beta normally or something like that. But for this particular observation here, I'm going to write V as an element of K. Define alpha V to be, okay, and I'm going to write it like this. Alpha times V, where this times here is multiplication in K, in the field K. And I'm just going to say makes sense because alpha, which is in F, is also an element of K. Yes, F is a subset of K, so alpha is also an element of K. So we just saw this done when F was the reals and K was the complex numbers. But let's see other examples of this. So examples. Let's take K to be Q adjoint cube root of 2. Okay, and I'm going to take F to be Q. This is a field extension of Q. So by what we just said, so Q adjoint cube root of 2 is a vector space over Q. So it's not a question mark, it's really just a statement, it's true. But once we have that, we can talk about bases, dimension, spanning sets, linear independence. We can employ all the machinery we know from linear algebra to study these field extensions. So, what's a spanning set? Remember, what do elements of Q adjoint cube root of 2 look like? They look like A0 plus A1 cube root of 2 plus A2 cube root of 2 squared plus A3 cube root of 2 cubed plus A4 cube root of 2 to the 4th plus dot 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 plus AN cube root of 2 to the n, where all the AI's are in Q and n is any non-negative integer. But we already said earlier that you actually do not need all these radicals, all the powers of cube root of 2, because you don't ever need anything higher than 2, right? It's just, for example, if I take the number 2 plus cube root of 2 plus 3 cube root of 2 squared plus 4 cube root of 2 cubed plus cube root of 2 to the 4th minus 3 cube root of 2 to the 5, I actually can write it as, so it's 2 plus cube root of 2 plus 3 cube root of 2 squared plus, now this is just 8, because cube root of 2 cubed is 2, so that's just 8, plus, now this, right, is 2 cube root of 2, because that's cube root of 2 cubed times cube root of 2. Finally, this is 3 times 2 times cube root of 2 squared, because cube root of 2 to the 5 is cube root of 2 cubed times cube root of 2 squared. So I get minus 6 cube root of 2 squared. I can then collect like terms, so I get 10 plus these two give me 3 cube root of 2, and these two give me minus 3 cube root of 2 squared. So I never really need any power of cube root of 2 higher than cube root of 2 squared. So as a conclusion of this, so 1 cube root of 2 and cube root of 2 squared is a spanning set. Of this field over Q. I don't know yet if it's linearly independent. I can't really answer this at this point. Okay? We need one more result, which we're going to get to soon, to be able to say if this is linearly independent. But one conclusion that I get from this is that I know something now about the dimension of this space. I know the dimensions at most 3. Because I found a spanning set that has 3 elements. If they're all linearly independent, then the dimension is 3. If there is some linear dependence between them, then a subset of it would do, which means the dimension would actually be less than 3. Okay? But I know at least that much. Let's do another example. Q adjoint square root of 5 is a vector space over Q. Okay, and here again I can give you a spanning set. Let's think about it for a second. 1 and square root of 5 gives you everything that's in this field, correct? Because again, this is, what is this? This is all the elements of the form A0 plus A1 radical 5 plus, I'm not going to even write anymore because we already discussed this, that you don't need any higher powers. So A0, A1 is actually in Q. So this is a spanning set. In this case, I can even go a little further and say that this is actually a basis. Because if it were not a basis, that means a subset of it would actually be a basis. But because rational numbers live inside this field, I at least need to be able to get all the rationals. So I definitely need 1 in my spanning set. I mean, just radical 5 wouldn't do, because any rational times radical 5 would give me an irrational number, so I wouldn't get all the rationals that live here. So that means that 1 has to be in the spanning set. But if I just have 1, then rational number times 1 is rational, so you would never get anything that involves radical 5. So that means this, no subset of it, the only 2 subsets are 1 and radical 5, no subset of it spans, so this must be a basis. There's no subset of it spans Q adjoint radical 5 over Q. This is also a basis. So the dimension is 2. Okay, and we will do a lot more of such analysis in the future.